Let's take a look at the integral of tangent of x with respect to x. Is tangent anyone's derivative? No. So normally with a trig function that isn't one of the 6 original trig derivatives, like we're trying to integrate one that's not the original 6, we put it in parentheses and we try to sacrifice the derivative of the inside of the parentheses, right? But even if it were in parentheses, I would need to give away a what to do the power rule to it. What's the derivative of tangent? Secant squared. So I would need to have a secant squared to give away in order to turn this into a power rule problem, and I don't have that. So we're kind of in a situation we've never been in before. And the way you do this is you use your quotient identity and rewrite this as sine of x over cosine of x. And what that will allow you to do is bring the cosine to the top.
Jared over there on the admin office.
Okay. Just bring the cosine to the top. Right? Now we can see this as to a power, and if we want to integrate a parentheses to a power, regardless of whether it's a trig function, I have to give away the derivative of the inside. So the derivative of the inside is negative sign. So I am going to have to balance this with a negative here and a negative here in order to appease our integral gods. And away these go, and that allows us to integrate the entire parentheses. And anytime we have a parentheses to a negative 1 power, it integrates up to what? Natural log. So we have the negative natural log of the absolute value of cosine of x plus c. So that's how we get that problem. So let's pause and see if we have any questions, and then I'm going to have you do one very similar. So now that we've integrated tangent, let's look and see what happens if we try to integrate cotangent. Same basic principle applies here. Cotangent is no one's derivative, and I don't have any other trig functions that I could use to sacrifice to turn this into a power rule problem. So we're going to use the quotient identity, split it up into cosine over sine, which gives us a little more to work with, because then we can pull the sine x to the top and look at it as sine to the negative 1 power. And then if I have a parentheses to a power, as long as I sacrifice the derivative of the inside, I can continue integrating as usual, right? So what's the derivative of sine?
Cosine.
So this becomes your sacrifice, or, you know, that's the appeasing of the integral gods there. And then if I try to integrate this, I can't with the power rule, so that means that it will become the natural log of the absolute value of sine of x plus c. So if you ever get stuck trying to integrate tangent and cotangent, that's how they are done. One way that people handle the trig functions is they just memorize them. I tend to think that with tangent and cotangent, it's easier to actually just see them and do them. There are two that are a lot harder to do by hand. Secant and cosecant are, you know. So I suggest that you memorize those two. And if you want to go ahead and memorize tangent and cotangent, you can. So what we have on the next slide are all 6 of the trig functions. And we already knew these two. We know those because we know the derivative of negative cosine is sine and of sine is cosine. We have now just covered these two, which you can do with the quotient identities. And if anyone's interested, you can look in your textbook and you can see where these were derived. And it's a really odd little thing where you take the secant of x plus the tangent of x and you pull it out of thin air and multiply it on top and bottom, and you distribute it out, and lo and behold, when you integrate, this is what you get. I recommend you just memorize it. So like I recommend you memorize that the integral of secant is the natural log of secant plus tangent, as long as you sacrifice the derivative of the angle, and that the integral of cosecant is the negative natural log of cosecant plus cotangent, as long as you sacrifice the derivative of the angle. So I do recommend that you memorize these, but if you would like to...
May we have your attention, please? Attention.
So as I was saying, if you don't want to memorize them, then you can look in your textbook. I'll show you where, and you can see how to derive them, but it does take quite a bit of effort. So I recommend that you go ahead and memorize these two. So I'll pause for a second, let you take notes on those, and then we'll do one more example, and we'll have time to work on our problem sets. So for our final example, we're going to look at a definite integral, which calculates the area under a curve. So we're going to look from 0 to pi over 4 of the square root of 1 plus tangent squared x with respect to x. First thing we should notice is that 1 plus tangent squared is a Pythagorean identity,
Secant
right?
squared.
Yeah. So 1 plus tangent squared is secant squared. So we'll change this to the square root of secant squared with respect to x. And the square root of something squared is just
It.
it. Just it. So we have from 0 to pi over 4 of secant of x dx, which is coincidental since we just got the formulas to integrate secant, right? Okay. As long as we sacrifice the derivative of the angle, and in this case we don't have to because it's a 1, the integral of secant is equal to the natural log of the absolute value of secant of x plus tangent of x. Right, you guys? Okay, and this time we don't have a plus c because it's a definite integral. So we're just going to take that from 0 to pi over 4. Then we're going to substitute pi over 4 in. So we have the natural log of the absolute value of the secant of pi over 4 plus the tangent of pi over 4. And that would be our f of b. And we have to say minus f of a. So we'll have minus the natural log of the secant of 0 plus the tangent of 0. And then we'll go up here and we will clean those up and see what kind of number we get from that. Does anyone know the secant of pi over 4? What's the cosine of pi over 4? Square root of 2 over 2? So if you flip that, the secant would be 2 over the square root of 2, right?
Which is 2.
But we don't have to fix it. Just
Well, you do that one because it will reduce. 2 over the square root of 2 reduces to square root of 2.
Okay.
Okay? So the secant of pi over 4 is just square root of 2. What's the tangent of pi over 4? Tangent of 45 degrees, you guys.
It's 1.
1 minus the secant of 0. The secant of 0 is the reciprocal of the cosine of 0. And the cosine of 0 is 1, and the reciprocal of that would still be 1. Plus the tangent of 0, which is just 0. All right, so take a moment, catch your breath, and make sure you understand where all that came from. It's no big deal. It's just, we got those off of our unit circle, right? Yes?
Yeah, unit circle is 4.
Yes. So the first one cleans up, and because it's a positive, I don't really need the absolute value, so we'll just have the natural log of the square root of 2 plus 1 minus, that's just the natural log of 1, right, you guys? But what is the natural log of 1? 0. So this goes to 0, and we just have the natural log of the square root of 2 plus 1. And the cool thing about this problem is you could check it in your graphing calculator by using second trace number 7. And that pretty much wraps up section 5.2.